Okay, I think. Okay, I think I'm screencastifying this. Give me 1 second. It says it's doing it, so I don't know. If it is, perfect. Okay. So let's rewrite the terms of this. And we have a little weird thing to deal with when we move our axis of rotation clear over here. If we're clear over here, we really only have one length to deal with. And our other problem, we had to deal with two lengths. But in this problem, we really only have a plus L because we're sitting on the other location. All right? So how about that? So now we're R squared, and we substitute in ML. And then we've got this D of R. And so let's pull the ML over to here. Now we've got this little thing cubed right here because we've taken the R times the R. So I'm running out of space, kind of. I swapped out the R now for the L. So if you can see all that. There we go. Remember, we take the R, we cube it, and then we divide by 3. That builds the 1/3 for here. And the reason why it's not L cubed is because we're still comparing it to that original L right in there. Okay? So I hope you can see that's the reason why. And I know we did 1/12 the other day, and 1/12 was a monster. 1/12 was an algebra monster. 1/3 is much, much, much easier, I think. Okay? So what I'd like to do today is really two things. I for sure would like to talk about the sheet we were working on yesterday in class, our little checkpoint. But before we get to the checkpoint, here is what I believe would be a really good use of our time today. We're going to have a quiz tomorrow. Oh, sorry. We're going to have a quiz on Thursday. But here's what I really like us to do right now. If we can find our unit notes on torque, I'm going to show you the problem that I would like to feature today. Since we're all here. Oh, Bree, glad you're here. Good job. It's all right. It's all right, man. Being here is the important thing. That's good. I'm looking for Wachia, but I do not see her, so. All right, my friends. Here is where my thoughts are going today. Well, when we talked about torque, we did this problem. Okay? If you remember, that's the problem we did. Find the sheet that has this problem for me, please. And pull. This is what I gave people yesterday. You probably did this on Cami, right? Right on, man. Right on. We'll finish her up today. Please let me know. Please let me know if you do not know
This is the sheet that I gave you all in class. It was a torque sheet. Okay, it was a torque sheet. With this torque sheet, we drew pictures of these. We talked about right-hand rule. We talked about cross products. Talked about the two conditions of equilibrium. We talked about how F equals ma is basically the same thing as T equals I. We spoke about Newton's second law of rotation and how it's good to find the calculation of an accelerated block falling down. And then we did three-body diagrams. And we came up with some really cool equations for this. So, is everybody able to locate the sheet that we did these on? Just holler out a, there you go, Cole. Holler out a yes for me. If you've got your sheet. You got it? Good. Shiv? All right, good. Shiv, you good? Nice. Nice. Benny, you good?
Yeah, I think so.
All right. Cole, did you find yours, buddy?
Yeah.
Right on. So we're on the back of this sheet now, people. We're on the back of the sheet. Now, here's the reason why I like these problems, ladies and gentlemen, is we're just not used to factoring in how a spinning object plays into things. When we did Atwood problems before, I think you all can agree that we focused on these blocks right here. Okay, so what I want you to do on the back of your sheet there is find the problem. I think this is on there. I think Cole's got his sheet. Is this problem on here? Atwood. Yeah, there it is. Okay, and it's exactly like this. All right, so put your free body diagram vector arrows on here for me, please. So we're talking about a scenario where, it says M1 is more massive than M2. M1 is more massive than M2. All right? So, we're going to say it's accelerating going down that way. We know this for sure, ladies and gentlemen. T1 and T2, they're the exact same tension. So these have to be the same size. Now, the one thing that I don't see up here that I don't like is that this should be longer than this. So make this one smaller. Make M2 smaller. That's the first thing we got to do proactively to solve this thing. Okay, cool. But we've also got to deal with this pulley here. This pulley has an M2G, and it's got this normal force acting up from the center of it, right? Let's call this MPG, mass of the pulley in the G. Right here. Well, let me tell you something. The sum of the forces in the Y, here cause acceleration. The sum of the forces in the Y here cause acceleration. The sum of the forces in the Y here, they don't cause acceleration. So how in the world is the pulley itself going to help us out? Well, look at what T2 is capable of doing to the pulley.
is capable of applying a torque to this pulley. So, when would we use a problem like this? Like, when is this helpful? That's when the pulley is massive. You can't assume that the tension is the same on both sides. What? I thought Matthew just said T1 equals T2. Well, T2 equals T2, and that is what we are in the position of looking at now. Let's isolate these things. Let's isolate these things. So we've got this T1 and we've got this T2 that are acting on the pulley. Free body diagram, easy. Free body diagram, easy. I think this free body diagram is pretty easy as well. We've got this R and we've got this R. So we know that somehow torque is going to solve into this problem. So let's go back to what we already know. Let's go back to what we already know about Atwood's equations. We know that M1G minus T1 equals MA. And if we're looking at this problem correctly, we're calling this positive acceleration. This downward vector, that's positive acceleration right there. So F equals MA. I'm calling this negative T1 up. I'm calling that M1A down. It doesn't matter. We can switch all these vector values, but this is just the way I chose to solve it on here. Either way, you're going to end up with T1 equals mg. If you wanted to switch all those values, that's not a big deal either. But if you keep down positive, it keeps T positive a little easier. Not really, but we're going to say it does. Always remember, I could have switched everything here. Could have switched everything here and just said, you know, it ends up being the same. All right, let's go back over to here now. T2 minus M2G equals M2A. What? Why is this one minus on this side? Well, because this is going up. Remember, this one is going up. Okay? So that T2 is now positive, minus M2G equals M2A. Remember, it's an Atwood's equation. What about our pulley? Woo! Take a look at our pulley. Okay? So, what would I do a little differently? I wouldn't acknowledge this. That's what I would write at first. F times R equals IA. And that is a torque. We know our pulley is spinning this way because it told us that one of the masses was bigger than the other. So one of these torques over here is going to be a positive torque and one's going to be a negative torque. So T1 ends up being our positive torque because it is creating. T1
is capable of producing counterclockwise rotation, which is possible. So, in a way, this is a positive torque, and this is a negative torque. And that's simply based on this and this, or this and this. That's what those are based on. Let me show this again, because that might be slightly confusing to people. Let's just focus on this, T1 and R. If this is just a bar right here, and I put a T1 on this, and it's acting at some distance R, this rotation, and here's my axis of rotation right here. This would tend to make the object spin this way. That becomes a positive torque that produces that. So I keep it positive TR over here. This T2, here's my axis of rotation now. Look at this. This is a T2 right here at an R. Well, if left on its own, that would cause it to rotate that way. That's a negative torque, which is T times R. So we're going to represent that with a negative over here. Because this object is spinning, it ends up getting its own alpha. Good job. Well, this object here also has some value for I, and we're going to use the I for a solid disk because it's a pulley. So we're left doing substitutions. Not for TR. We're not doing substitutions for TR. We're going to now put in 1/2 mr squared. So that is our I. Mr. Matthew, what is this? Well, let's take a look. Linear, linear, linear. Ah, that one was rotational. We're going to substitute it out. And that's what we're doing. So because A equals omega R, or alpha R rather, we just substitute it in. That gets rid of anything that's rotational, because you can't have linear terms and a rotational term. So we've got these R's now, and all these common terms. Oops, gotta leave yeah, they all cancel. Woo! So the differences in those tensions are going to cause an acceleration. Guess what this means? Guess what that means? T1 can't equal T2. Because if it did, if they were the same number, you'd have no acceleration. There. You just proved that they can't equal one another. Sorry if my antics here got super sloppy. But that is what we need to understand. So Matthew, how can I solve for T1 or T2? Well, here's what I like to do. I know this equation is true. I know this equation is true. I know this equation is true. So, if all of that is true, I think you guys know what I'm getting ready to do. Don't write all of this down. I know you can do algebra, but here's what I literally did. I just substituted that in for, oh, it's made a mistake.
I just substituted T2 in for that, and I substituted T1 in for this. That is what you're seeing is massive substitution. Just write this down. Woo! Ladies and gentlemen, if I can establish that M1G minus M1A is T1, and then M2A plus M2G, I've got to distribute the negative amongst terms, FOIL method style. I then end up with understanding that the acceleration in that system, in a linear sense, is dictated by the differences in the hanging masses, M1G minus M2G. But the mass of the pulley has a voice in the acceleration. And at the end of the day, ladies and gentlemen, we have proved nothing new. At the end of the day, we've proven nothing new. F equals ma, Newton's second law. We get the net force that causes our pulley system to move, which is the differences in the masses. M1 is bigger than M2, so that'll give a positive number on top. And we just combined all the masses below. M1 plus M2 plus M3, which in this case is the pulley. But because of the way rotational inertia works, only half of the mass of the pulley gets figured in because it's being balanced from the center. Woo! That is an awful lot of stuff to keep in mind. That's an awful lot of stuff to keep in mind. Ladies and gentlemen, I think what I would like to finish by saying is this. We know that rotational kinetic energy comes from 1/2 mv squared, where we substitute in for the v with rotational terms. I think we're all very comfortable right now knowing that the kinetic rotational energy is 1/2 industrial waste squared. All right? You do get some interesting calculus relationships from all of these objects. These will also be given to you on the AP exam, and none of them are like really all that wacky. Work equals the integral of force times a radial vector. In a circle, work equals torque times the angular distance. Okay? So what we're saying is if we have something that will spin in a circle, what if this force is variable? If that force is variable at this distance r, that's still torque. And then the distance it goes through is still theta. So we would just treat it as such when we integrate. Power is work divided by time. Or it's force times velocity. It's both of those things. It's missing an equal sign. Well, power could also be torque times omega, because this is like a force, and this is like a velocity. And then, of course, kinetic energy equals this. Okay? Were those on your sheet of paper? I can't remember. You see. Oh, got it. So, your space on there is for linear rotation. So just write those three on there. And then we're doing great. So I'll give you a second to catch up and take a breath here.
right, so ladies and gentlemen, there's some other interesting calculus relationships on the slide that we're going to talk about later. I'm going to de-emphasize the calculus for our quiz tomorrow. Well, I'm sorry. I misspoke. Let me go back.